Welcome to this talk on 6G and AI. My name is Sasu Tarkoma. I'm visiting professor at the University of Oulu in the 6G Flagship and also professor of computer science at the University of Helsinki. And today we have the exciting topic that how we can integrate AI and 6G technologies. So that's an exciting direction that is very much going forward at the moment. So today we talk about the network, the distributed environment, applications, and how can we support the applications and also the network with AI. And we consider the current situation. So we have logically centralized cloud services which are heavily used to provide applications and services. So we have the networks supporting with the data communications, and then we have the higher layer, the cloud, for the intelligence, for data processing. And much of this is actually quite centralized. So we have the big clouds where data is gathered and stored. And now we can see that this can be fairly efficient given the big data centers and focusing and centralizing the processing there. But also we then face the challenge that all the data is gathered with the same logically centralized location, place, and also we see that the local resources may not be used very efficiently. Also, given that there may be needs in terms of security, privacy, so we have to consider local operation more carefully. And that's really about the next steps in edge intelligence, so having more distribution in how we process data, how we organize AI for the applications. And the big question is that how can the network support here? So how can we, in a way, design the forthcoming 6G so that it would accommodate the local data needs, local AI processing needs of users and applications. And that would then enable more privacy since it's local. It would enable more security, again, with the locality, and then having more efficient use of the resources we have on the devices, for example, in Internet of Things, at the edge of the network, and in the region as well. So that's the main goal of edge intelligence, to enable such organization that the network can accommodate distributed use of resources in a very efficient manner. And we are going to this direction. And now the latest step here is to consider language models, large language models, as well, how they can be integrated into this distributed system. And to this end, we have had for a long time the vision of the 5G and 6G network that would accommodate the distributed agents, AIs, and the use of these when it makes sense, where it makes sense. So we speak about the edge cloud continuum that contains all the different processing elements in the network. So then devices, different network elements, edge servers, and then also the faraway cloud. And we need to consider that how to place elements over this edge cloud continuum in an efficient and secure manner. And the key step here is orchestration. So how do we orchestrate the network, its configuration, orchestrate the applications over the network, and ensure that all the requirements of the users and applications and also the network are met. So it's an optimization problem. And we have been looking at this for many years. It's a very rich environment in terms of the research questions. And we have now fairly good understanding that how to best operate and organize the network and the orchestration for meeting these requirements. Lots of optimization is needed. And now looking at all the different components, enablers for creating these distributed networks with AI, we see that there are many different possibilities for the implementation. And this slide illustrates these different components, these enablers. So we see that we have 4 categories for the enablers. We have training of models, illustrated here on the left-hand side. We have inference, so the use of machine learning models on the right-hand side. Then we have caching, so reusing existing results, making systems more efficient, more optimized. And then we have offloading. So how do we distribute the compute, the processing of the different enablers? And altogether, we have this rich environment, many different components, and these provide, in a way, the basis for the network that integrates AI and is able to use AI for its internal operation and also for the applications as well. And now one key challenge is that how do we orchestrate this network based on these elementary enablers? So how do we choose what enabler is needed, and how do we configure that? How do we place it? How do we maintain the configuration? And so on. So these are topics that have not been explored so well yet. So that's a new direction, that how do we automate the generation of these networks built on these basic enablers. So that's a very rich environment, and not only can we consider the generation of networks and network configurations, we can also consider generation of applications over the network. And that's something that we have been exploring, that how to generate networks, how to generate applications with AI, and AI being integrated into the network. Now, given language models, LLMs, we have two new capabilities emerging from their operation. So one is task planning, task management, so that we can use LLMs to decompose a given instruction, given input into more elementary tasks. We can then select the AIs, the models to be used for each task. We can do task execution, and then we can combine the results for an overall solution. So task management is one exciting new capability. Then we can also have LLMs as tool users. So they can select the tools from an available set of tools. They can also be used to generate new tools. So we can generate code when needed, and these capabilities together provide a very interesting foundation for supporting network generation and also application generation in the 5G, 6G context. So we have been taking these as ingredients for future network designs. So task management, and then tool use and tool generation. And to this end, within the 6G flagship, we have been discussing among the community that how LLMs, language models, can be used within the 6G context. And there's been a lot of related work recently appearing in this, and a lot of ideas that where can we go with new technology. And we have together within the community written a white paper on the topic. So you see the title page here, so large language models in the 6G enabled computing continuum. So that's our white paper. It's now released, so you can see also the link to the white paper. And the document goes through the state of the art in this area and our new ideas on how LLMs can be integrated into 6G. What are the potential benefits in terms of being able to generate new applications, for example, and then also what risks are involved as well, for example, in terms of security and privacy, and how to mitigate those. So the white paper goes through these different concerns, different viewpoints. And to give you an idea that how the architecture for integrating LLMs into 6G is shaping up, so we have this figure. So here you see at the top part, we have the control plane and the user plane. We have also the higher level application logic here being illustrated. And the control plane and user plane are supported by the AI-enabled radio access network and also core network. And now orchestration plays a key role here in how to place and use AI across control and user planes and also with the applications. And we have now worked on the design of an AI interconnect, which is now responsible for doing this and helping with this orchestration, doing AI selection, placement of different components, also configuring of these components, doing task coordination, having communication and routing as fundamental primitives, and also having safeguards and audit trail as well for accountability and also explainability as well, that how AI is being used in the system. And the AI Interconnect goes through the different layers, different levels of distribution in the system. So it's a cross-cutting entity. And to give some more details on AI Interconnect, how this element works. So here you see an overview, having the radioax network and the core network at the bottom. We have the orchestration and optimization. In a way, middle of the system, we have intent and semantic communication. So we are using publish, subscribe, and trying to make as flexible communication between the elements as possible. And this is envisaged to support software agents as well, so that we have loose coupling of the components of the agents supported by intent-based messaging and publish, subscribe. And LLMs power this system. LLMs are used when it makes sense, and they are distributed, and the distribution is governed by the scheduling and orchestration mechanism. And we, of course, consider the different security, privacy, and operational requirements for the placement and activation and use of these AI components. So that's the basic idea here. And we want to keep the use of the system as simple as possible, especially for the endpoints. We want to separate concerns so that we have task and intent analysis, and also we do decomposition of the inputs into smaller components, smaller tasks, and then use the orchestration, use also the semantic pub-sub communication for the decoupling in the distributed system. We also enable what we believe that would be future-proof approach, that we can change the models when it makes sense, so that when newer models are introduced, we can change those as we go. So model selection is also one important feature as well. And then making also this system deployable across wide variety of different physical networks and systems. So we leverage this kind of overlay thinking, that it's an overlay that can be then deployed over 5G networks, over forthcoming 6G networks, also other kinds of networks as well. So we are not deeply integrating this with any specific network technology, but can accommodate different kinds of technologies. So now going more into detail, that how are we implementing this publish, subscribe, semantic intent-based communication. So we start from a supply of compute resources, supply of language models. And we, of course, do model selection based on the requirements. And then as a key component, we have a neural router. So we have designed and also implemented a neural router design that has two layers. One is baseline neural routing, which is able to accept incoming subscriptions and also publications, events, and then do language model-based reasoning of these, and then matching content, matching events based on subscriptions. And the idea is that we would be able to accommodate almost any kind of subscription, and we would reason about the input requirements, criteria, the intent, what is needed, and then be able to provide matching information, matching events to the subscription. That's really the idea. And language models are very good at this kind of reasoning of the input, so that they seem to be a suitable basis for doing this kind of very expressive matching of content to subscribers. Then we have a higher level, which is about neurosymbolic operation. So here we introduce complex event processing. We introduce more elaborate reasoning steps as well. And also application state can be also supported with this higher level. So we go from elementary routing to a higher level, more complex operation. And we then have multiple routers So it's a distributed environment. We can have multiple routers. They are configured into a overlay network topology, and we then can accommodate these subscriptions. So intents to receive information, but also we go beyond simple routing with this neurosymbolic layer so that we could also have an intent for an application. So that we just explain that to the system that we would want to have an IoT application combining IoT data sources, events, some background information, having certain processing logic that would need to be provided. And then our system can first, through the task decomposition, identify the elementary subscriptions and data needed, and then the higher level, more complicated, demanding algorithms and data needs as well. And then put together and deploy this application that is specified in the intent. So that's one of the goals of our work, that we would go to this kind of intent-based networks, intent-based applications. And so we have now the subscription coming in, and we, of course, process subscription state in the distributed environment. And when we have a publisher of information, that information, if it matches the subscribed intent, we deliver that. So here you see how this works, and we can then deliver accurate information based on the intent to the subscribers. And this happens in a similar manner on the higher level as well, in this neurosymbolic layer. But there, the operation is more complicated and more demanding. And this complex event processing is one feature we have been working on recently, and we have a new preprint on the current results regarding how complex event processing, CEP, can be implemented for multi-agent systems. So there is one reference outlining our work. Then going now to an example. So we have the neural router and we have an intent. Let's say that we want to subscribe to network quality events given the ORAN XApps API, and we want to do a basic analysis for network insights. Let's say that we would want to have the average data transfer sizes and such information, let's say for last events or any number of events, and we would need to have these certain intervals. So that's an intent. We give this intent to the system. We give it to the neural router, and then it will, using both the neurosymbolic layer and then the baseline neural routing layer, it will figure out that what data is needed, what kind of subscriptions are needed, how to structure this intent into a more logical form. And we have this specification then that is implemented to realize this intent. And here you see that we have a subscribe and then LLM operation as end result. And now where we can optimize is that we can do further processing. So we can do local and distributed optimization. And one important optimization is to transform LLM operations into code. So here you see that we have transformed the LLM operation into Python code. And we can then deploy this code, and it's much, much more efficient than the LLM operation. It's also more sustainable. Actually, when we run this on a local deployment, we see very significant performance difference between the LLM operation and then the code. So code would be preferred when it can be produced in a reliable and secure manner. And this gives you an idea of the system. So we go from the intent to formal representation of the intent, then identifying the different elements, the operations, optimizing those, and then activating those in the distributed environment, and then that then renders the intent. And we have been implementing this vision and then doing experiments. And today we are also creating a test bed between Oulu and Helsinki, in which we explore these neural routers in more detail and with a practical and experimental mindset. So we have two sites, and we have these neural routers that we are exploring. We have experiments ongoing, and we are also exploring different kinds of applications, that what can we then generate and deploy over this distributed testbed. So it's a very exciting direction. There are many application domains that we can consider benefiting from such generative approach, both toward the network and then also toward the applications. So I would like to invite everyone to also join this kind of experimentation. So we are very happy to tell more about the work and about the experiments. So thank you very much. This was a talk on AI and 6G, how to combine those. Thank you.